All right, welcome back, everyone. So continuing on from last time, we were starting our unit on neural networks, and our motivating problem is this simple one where we have a binary labeled data set with two features. And this is the scatter plot, which shows that the data is not linearly separable. So if we tried a linear method like logistic regression, that would not work well. There's really no way we can place a hyperplane that works well. We've also talked about feature transformations, and those can work well. For example, with a similar data set where you have one color closer to the origin compared to this other label out here, if you create a third feature, which is essentially like the squared radius, then in that new three-dimensional space, you can easily classify the data. You can find a hyperplane that makes it linearly separable. So the idea here is that feature transformations are very powerful, but the trick is choosing a good one. So essentially, we can think of neural networks as a multi-stage classifier where the last stage is going to be a linear method, but then the earlier stages are building some kind of feature transformation that makes that linear classifier perform well. So the method that we're starting with is a two-stage approach. The first stage is going to learn 4 transformed features, and then the second stage is just going to do linear classification on those features. And the way that we generate each of these features is as the soft output of a linear classifier. And for a visualization, so for example, this is one of the 4 features. This would be the classifier decision boundary associated with that feature. And we know that when you look at the linear score on one side of the classification boundary, it's positive, on the other side it's negative, and right on the boundary it's 0. And then we know that if you put that score through our logistic sigmoid, it saturates either at 1 or at 0 as you get far from the origin. And so you can roughly think of this one feature as being close to either 1 or 0 here, and then close to the counterpart 0 or 1 here. And so we've constructed 4 such features using these 4 different linear classifiers. And if you think about them all together, generating a 4-dimensional transformed feature vector, for example, maybe it's 0 on this side and 0 on this side, and 0 on this side and 1 on this side, and you get a certain pattern. So wherever you are, whichever one of these facets you're in, there's going to be a particular binary pattern that is implied by those soft classifier outputs. And it's exactly that pattern that the second stage can react to. It can basically learn a weight vector, which is collinear with this pattern. And then that means that the output score within this region is going to be very high, and within other regions is going to be much lower. And that's exactly what's happened. So, we're not choosing any of the weights. We'll talk about the training in detail in just a moment, but we're training this according to our cross-entropy loss, or binary cross-entropy loss, same as always. And so these are all learned things. It has learned to put 4 boundaries here, and then it has learned some second stage classifier weights, and these show the heat maps. So for this boundary, it turns out that to this side, Z was positive, and so that means as you get further here, the soft output gets closer to 1, and this heat map shows us by the color. And then for this boundary, one is on this side for this boundary, one is on this side, and for this boundary, one is on this side. And so that gives us this pattern right in the middle. And then when we look at the weights that were learned for the second stage, you can see that wherever there's a 0 here, the corresponding weight is negative, and whenever there's a 1, the corresponding weight is positive. And finally, the second stage output, if we take that real number score variable z, and we put it through another one of these sigmoids, then we can get another soft output, which we're plotting using this heat map. And so it's giving us high confidence of the green class wherever this is dark red, and high confidence that it's not in, or high confidence in the blue class wherever it's in this white region here. And these were just, everything was learned from the data, and if we run the notebook several times with different random seeds, you'll get different placements of these 4 lines, different weights, and so on, but you'll get a similar kind of picture at the end. Okay, so that's sort of a review of where we were from last time. Any questions on this? Is it making sense? Okay, so we're just going to get into some of the details now of what we've done. So we can first draw this as a block diagram, starting with our 2 features. And these are going through a linear transform, or affine linear transform. So we're taking that x, we're multiplying it by a matrix of size 4 by 2, plus adding 4 learnable bias coefficients, and that gives us our these scores here. And the way that people name this, the hidden layer is this stuff that happens sort of as the first stage, and then the output layer refers to the second stage. So we're using subscript h for all the hidden layer parameters. So we have like hidden layer biases, hidden layer weights, hidden layer outputs. Sometimes people call these logits also. And then this is the logistic sigmoid function that gives us the soft outputs of the linear layer. And then those are essentially the outputs or transform variables that go into the final layer, which is nothing more than binary logistic regression. So we have a weight vector of WO, we have a scalar bias BO, we have a single score ZO, real number, that goes through a sigmoid, and then finally we get a soft output, something between 0 and 1 for AO. And so that's the block diagram. The main equations then, X gets processed to those scores ZH. The scores get processed by a nonlinear function. In this case, it is a sigmoid. And by the way, the notation here, just to point this out, so this is a vector. And this is, we usually think of this as a scalar input, scalar output function, our sigmoid. But here we mean that this is applied independently to each element of this vector to give this here. So this is, you could say, a separable function applying identically to each of the components of the input. And then in the output layer, we have, again, a linear portion. And this is optional, this last stage here, but we use this in order to make the heat map here. And that's our final soft output. Sorry. Okay, so these AH, you could say, are our learned transform features. Okay, so basically, this has the structure of a 2-stage feed-forward neural network. And the key kind of high-level structure of a neural network is alternating linear, nonlinear stages. Linear, nonlinear like this. So this is also called a multi-layer perceptron. All right, any questions on this? Yes?
So how this applies to the slide above, the first linear transform would be like where we place the lines?
Yeah, so if you think about it, so this matrix here is a tall matrix, right? It has 4 rows of 2 coefficients. So, so for each one of these classifier boundaries, you need 2 numbers to say where it's pointing, and then you need 1 more number to shift it. So that's kind of like there's, in the first row of this is a scalar that corresponds to the first row of this, which is 2 weights and 1 bias. And we said, we talked about this last time, that we chose 4 kind of arbitrarily. We could have gotten away with 3, but not 2, but we could also use like 5 features and so on. So you could have, a taller matrix here if you would like. Okay, yes?
So is it that the last layer is going to be linear and the preceding layers are nonlinear, or does it have to be nonlinear, then linear, then nonlinear, then linear?
Well, okay, so you can see that here we have a linear layer, here we have a linear layer, but then this one is nonlinear, and this one is nonlinear. So I'll talk about kind of choices we have for this and choices we have for this. But let's first do a thought experiment. What if I took this out? I just removed that. What's going to happen? What do I have as a result? So if I take out that, and you think of cascading these 2 operations, what do we have in the end? Well, I don't know. I mean, we haven't really talked about noise or not noise, but the question is, is this nonlinearity essential or not? So, Darren, you kind of nodded. Why do you think this is essential?
Without it, we're just doing a linear system in terms of the original features.
Exactly. So this is an affine linear system. This is an affine linear system. If there's nothing in between, you're just cascading one and then the other. That's just another affine linear system, right? Meaning a matrix multiply and a shift. And if that's all we're doing, we are back to logistic regression, right? It's just like kind of an overly complicated way of doing logistic regression where you have like individually adjustable stages, but at the end of the day, you could represent all of this by one weight matrix and by one bias vector, right? And as we know, like that's not going to help us with this data set because the data set's not linearly separable. So having these nonlinearities in here is essential. Without it, it's not going to be a neural network. Okay, so any questions on that point? Okay, so what about this last one? Is this essential for our task at hand? This is what is taking these scores, which are numbers, on the real line. We know that score of 0 means the most uncertainty about what class the input is. So is it really essential to have this sigmoid here? What do you think? So let's say I wanted to make a decision, a hard decision. I want to, choose green or blue. I want to choose label 0 or 1. Do I need to have this sigmoid here to do that? I see people nodding their heads. Anybody think that we don't need this to make a decision?
Shouldn't you be able to do it just with the scores?
Exactly. We can just look at the sign of this. If the sign is positive, we say 1. If the sign is non-negative, we say 1. If it's negative, we say 0. So this is not really essential. This is optional. It's transforming our linear score to a soft output, but we could have gone right from here and just thresholded it to get a hard output if we wanted. So the only reason we really had this is to kind of make this plot, this heat map. That's really the purpose it's serving for us. Let's ask another question. Let's get into the training a little bit. So these are the things that we need to learn in this system. You can see we need to learn this weight matrix, this bias vector, this weight vector, and this bias scalar. Those are all the learnable parameters. Everything else is fixed. Sigmoids are just fixed functions. So let's take all our learnable parameters and put them into the vector theta. And as always, we need to fit these parameters with our training data. We have n samples. As always, these are now binary. These are two-dimensional feature vectors. And essentially, you could say like, well, we're doing logistic regression. There's different, I guess that is in fact how we trained it. We trained it according to logistic regression. And so essentially we're using this model which has our logistic sigmoid. So we're using the model, the probability that y equals 1, given the input feature and all our parameters, is 1 over 1 plus e to the minus z. This is our sigma. But here's what's different than what we've done previously. Now the function that takes us from our input x to our final output score z is not linear. It's nonlinear because of these sigmoids. Right? If we take these out, then we have linear regression, and in fact we have binary logistic regression. So this is what's really different now, is that this function f is describing the network from the input all the way to the output score, which is nonlinear. That is why it's interesting. That is why it can do this, fancy nonlinear classifier boundary and classify this particular data set well. Okay, but everything else is pretty much the same as before. We're going to do maximum likelihood, as always. We're going to use our cross entropy loss, binary cross entropy loss, we derived it to be this. We're going to use gradient descent or some variation of gradient descent to figure out what these parameters are, the ones that are going to take downhill gradient steps until we get to hopefully the minima. Now the key thing is, because of those nonlinearities that we stuck in the middle, this loss function is no longer convex in theta. It is actually convex in these parameters, but it is not convex in the parameters on the other side of those hidden layer sigmoids. And so as a result, a lot of our intuitions from before, from Unit 6 about convergence of gradient descent and all that stuff, we can't rely on them anymore. There could be multiple local minima, some of them could be bad. All kinds of bad things can happen. It's not clear that even if we get to some local minima, it's not clear that that's good or bad or that it's the global one. So there's a lot now that's more complicated than before, but fortunately there's I guess enough practical wisdom out there that things have been implemented very nicely in off-the-shelf software, and you can run it, and we'll describe how to do that later this unit. And you can, if you just follow basic good design principles, you can get a very good solution to this problem. Okay, so we'll get into some of those details later, but I just wanted to say, on one hand, it's very similar to everything we've been doing so far: maximum likelihood, cross entropy, gradient descent, all that stuff. But the main difference is that it's no longer a linear model, and that it's no longer a convex loss. Yes?
So why is capital W and B convex with the other two arms?
Oh, okay. So why are these? Yeah. So when we come back over here, so if we, let's just say that these parameters here are just generating, this is like some nonlinear transform applied to the data, right? And so at this point, we just have logistic regression. And we know that for logistic regression, it's convex in these parameters. But when we look back through these nonlinear sigmoids, we have these other parameters on the other side of them, and because of these nonlinearities, you can show that the loss is not convex in those parameters. So that's our issue right now.
Thank you.
Yeah. Okay. All right. Is this everything kind of making sense? Any questions here? Okay. All right, so maybe let's step back and talk a little bit more generally. Why is this called a neural network? Well, if you look at a very simplified model of biological neurons, basically each neuron has these things called dendrites, which are like things that take in input currents from other neurons. And then the soma is like the cell body that collects charges that come in from those other neurons, and they accumulate in that cell body. And then once the accumulation of charge crosses a threshold, then this neuron sends out a charge to the other neurons that is connected to through what's called the axon. And so, roughly speaking, if you want to, model this mathematically and not really taking into account the time domain, but just the charges, if these are the different levels of charge coming into the cell, maybe there's some different way in which they are weighted, and then this is the total accumulated charge. And then we have a nonlinearity, which is basically looking to say, is that beyond a threshold? If the charge is beyond a threshold, then you put out something large. If it's not, you don't put out anything. So this is, roughly speaking, how you can model one of these biological neurons. But this is also, if this is a sigmoid, then this is exactly logistic regression, right? But it's also, you could say, how we're modeling each one of these. Linear followed by some sort of sigmoid. So that's essentially how our method is you could say an artificial neural network. All right, any questions? All right, so some history then. So these biological models of how neurons work, these were being studied already in the 1940s, mainly for biological reasons at the time. But then in the 50s, people started thinking about how to apply these artificially. And so we had like the first single layer artificial network, which really is, like I said, more like logistic regression than what we think of now as neural networks. And there were some very early computer implementations, so this is very crude computing, maybe even with vacuum tubes. And then we have issues at the time. Linear classifiers, as we know, are quite limited in what they can do, and compute power in these days was limited. So not a lot of progress was made. But in the 1960s, as computers started to get a little bit more powerful, people needed to come up with more organized ways of updating all the weights in these artificial neural networks, and they came up with the backpropagation algorithm, which we will cover maybe even later today. And so that's super important if you are training multi-layer networks. And this was sort of, you could say, the first wave of AI. And there's a lot of excitement then. But then eventually there was like too much hype relative to the excitement, and so it kind of got out of popularity. And then there was a second resurgence or recurrence of all these ideas in the 1990s. That was like the second wave of artificial intelligence. And again, people got super excited throughout the 1990s about AI. Lots of additional progress was made. But again, it didn't live up to the hype, and so by the early 2000s, like if you were working on neural networks, you were not very cool. You seemed like really, like, come on, man, like, get with the times. But then a few people did stick with it. Some of those people are very famous now, like Yann LeCun and other people that were already, working in the 90s, but they kept working on it, even though there was a lot of doubters. And then about in the year 2012, because of increases in computational power and also increases in data availability, they were with more or less the same, a few new tricks, but more or less the same ideas. They were able to make big progress and all of a sudden far outperform other methodologies for things like speech and image processing. And so those were the first big breakthroughs. And then once people realized the power of these methods, they started applying them to many other fields. And as we know now, there's just a huge craze about AI and everything. And of course, there's still a question about, how much is hype and how much is reality. But anyway, we are now in the third iteration of AI. All right, any questions? Okay, so let's come back to these two-layer feed-forward neural networks, talk a little bit more generally. So again, we have an input, which is, in general, we have D raw features, and then we have a hidden layer, which is going to have, this is for each of our hidden layer nodes. We have a affine linear transformation from the raw input feature. So this is the affine linear part. Then this is going to go through a scalar nonlinearity to give us what we call the activation function. So A is the activation, and then the function H that computes it is called the activation function. And we have, so this is like, there's D of these units here, and then I'm calling the number here DH, the number of hidden units. This is something that we have to choose. And then we have an output layer. And the output layer, we don't have as much choice of. It really depends on the task that we are solving. So we know that if you're doing, for example, binary classification, then you just really want to have one score here, right? You're making one classifier output. If you're doing classification of 3 or more categories, then the way we set up things in the past is the one versus rest idea. And so you would have like 3 output nodes. And the first one would be like, the size of that one would be how confident you are that it's in class 1 versus class 2 versus class 3. Okay, so that's we have the hidden layer, the output layer. The output layer, again, you have, let's see, so this is the linear part. So the output layer one, you again have some linear processing, and then you have, you may or may not have an activation. So this, we'll call it HO, maybe make it this color, HO. And this is optional. So sort of like we talked about before, in this picture, we talked about why, we were talking about why this is really optional. And so it's true in general. If you decide to use an output nonlinearity, you have to make sure that it works with your application, with your task. So if you're doing, for example, logistic regression, then a binary logistic regression, you could put a sigma here. But if you're doing regression and you're trying to predict a real number and you put a sigmoid here, then this is only going to allow outputs which are between 0 and 1, right? So you'll never be able to predict anything outside that interval. So it could be disastrous. So you really want to choose this to match your output. And actually, I think in most cases you could just leave it out because it's enough. If you have this is usually enough to train your system just with the linear output and not actually put it through nonlinearity. Okay, so this is, it's optional. If you use it, it has to match the loss. And same thing with the dimension of the output. This is really determined by your task. It's not a free parameter. Okay, and here we're talking about 2 layers, hidden layer, output layer. In principle, you can use more than 2 layers. We'll talk about that more at the end of this unit, but for now, we're just going to focus on 2 layers because that's enough for now, enough to talk about. Okay, so I want to point out something about this block diagram because when I first encountered these block diagrams, I was really kind of confused because these maybe I shouldn't even call it a block diagram. These are really difficult from what I always saw as someone trained in ECE. Whereas in ECE, you have like, you kind of think of like a system being some sort of box, and then you have like, some signals going through the system using arrows. But here, it's almost like the arrows are the system, and the big blocks are like the variables. So just keep in mind that in computer science, they have different ways sometimes of building diagrams, and they might have a different meaning than we're used to. But basically what these are showing is you could think of roughly as your input nodes, so you have D of these. If you had 4 hidden nodes, it'd be 4 circles there, and if you had 2 output nodes, you'd have 2 there. Okay. All right, any questions so far? Okay, so again, I think it helps to put some math behind this. So this is a similar picture of what I drew last time, except that I think really the only thing has changed is I was a bit more general on what happens at the output here. So this linear transformation, we've seen this equation. It's the same one we saw last time. This is our nonlinear activation. Again, this applies element-wise. Oh, I actually wrote it over here. And we have an output layer that could give us, multiple outputs, depends on our application. And then we have an output activation. One difference is that while these almost always act in an element-wise fashion, the output one actually could involve, it could be like a vector in, vector out. So in fact, the one that I've drawn here is if you did, you could implement binary classification with 2 outputs in the sort of one versus rest fashion. It's kind of redundant, but you could say that this is 1 versus the rest, this is 0 versus the rest. And if you did that, and if you plotted the multinomial logistic loss, it looks like this. It's kind of like a 2-dimensional sigmoid. So in general, if I have k different output classes, and I'm doing, I have the softmax function in here, I could have like a k by k type of processing from my outputs to my soft outputs. Sorry, my linear scores to my soft outputs. Okay, so again, this is just taking a peek again at the math behind the 2-layer network. Any questions here? Okay, so let's talk about common choices for the hidden layer activation. So we've seen one so far, it was the sigmoid, and here's a plot of the sigmoid. And one of the things you notice about the sigmoid is that you can never get something below 0, you can never get something above 1, right? So the output is basically bounded in this range. And also the output is not centered. So when the input is 0, the output is 1/2. Okay, so there's a variation on the sigmoid, which is really just kind of a shift in scale of it called the hyperbolic tangent. And the hyperbolic tangent is just 2 times the sigmoid minus 1. So as a result, it's the same shape as the sigmoid, but now it goes from -1 to 1. And so this one is obviously bounded, but it's also centered, such that when the input is 0, the output is also 0. And this centering makes it work a little bit better when training networks usually. It helps to decouple a few things, and that just makes the training a little bit easier. But roughly speaking, both of these work okay with 2-layer networks. And there's a very popular alternative called the rectified linear unit, or ReLU. And this one is quite different in that it is, okay, so the function is just, it's either, if the input is negative, then the output is 0, and if the input is positive, the output equals the input. So this one is, while these are bounded, this one is unbounded. And while this is not centered, this is centered. This one is also, well, I don't know if you could say, it's not symmetric. I don't know if we want to say it's centered or not, but it's not symmetric. But we'll talk about, there's particular advantages to this ReLU, especially as you get to having more layers than 2 when you have deep networks, and so there's particular reasons why you might want this, but it usually works pretty well in shallow networks too. So these are some common choices. There's actually many others. We will see a few others later. All right. Any questions on hidden layer? So this is a design parameter. You don't necessarily know which one is going to work better. You can just try different ones and see on your data on like your test set which one works better. Okay, so now we have the output layer classification. And like I said before, this one really depends on the task we are applying our network to. So if we're doing binary classification, as we know, the final output, we don't really have a vector, we just have a scalar, ZO. And if the scalar is positive, that means we have some confidence that the input is from the 1 class, and if it's negative, we have more confidence from the 0 class. So there's 2 options here. One option is to don't use any output activation function. You just output that linear score directly. The other option is that you put it through a sigmoid. And as a result, the network is actually outputting these soft outputs. Okay, that's actually what we did in that demo. Okay, so that's our sigmoid here. So those are the 2 options. Other than that, no other options really make any sense. Okay, any questions on that? Okay, so now let's say we're doing multi-class classification with more than 2 classes. So now, the way we set this up is our final output is going to be a vector of dimension k, the number of classes. And one option that we have is to use the softmax function, which is the same thing that we saw when talking about multinomial logistic regression. So it's basically like a multidimensional sigmoid. And the other option is to use no output activation, just output the vector z0. Okay. And then another application that we've seen a lot of is regression. If we just take the general case where we have k different targets for k is 1 or more, then the final output will be a vector of reals of dimension k. But in this case, we really don't want to use any output activation function. We just output that directly. Okay, so that's how we typically choose the output layer activation. Any questions? Okay, and now let's talk about the loss functions. So again, the task determines the loss and the optional output activation. So again, starting with binary classification, the way that we've approached this with logistic regression at least is we have this likelihood model, logistic sigmoid, and so we derived that our loss is this negative log likelihood function. We called it the binary cross entropy loss. But if you notice, the way that we've always done the derivations is we've assumed that the inputs to our loss function are those linear scores, ZO, right? If you have decided to put onto the end of your network this sigmoid, then the outputs are no longer ZO, they are this sigmoid. And so let's give them a name. Let's say that the outputs coming out of the sigmoid, we'll call them AO. And so now, there is a different way of expressing the binary cross-entropy loss in terms of those AOs. And so here you can see it is a function of the AOs, but not the ZOs. Okay. It is exactly the same thing. So in other words, if you plug in this expression here and you simplify it, it will come out like this. So just a different approach to get the same thing. But it's actually this version that looks a lot like cross entropy from information theory. This is really where the name comes from when we talk about cross entropy. Okay, so you have two options. I'll talk about the implementation in PyTorch in a few more slides. But basically, you have to choose the loss in a compatible way to how you built your network. So if your network is outputting ZO and you put it into this loss, it's not going to work, right? Because this is expecting the activations. On the other hand, if your network is outputting these sigmoids and then you plug it into this, it's not going to work. Right? You have to match your loss with your network outputs. Okay. All right, so that's binary classification. Any questions on this? Okay. So then we have the multi-class case. K greater than 2 classes. So the likelihood that we derived used this softmax. And so again, we have two options for how we could write the loss. The first one is to write the loss, this is the one we derived, to write the loss in terms of the z variables. This is how we saw it before, but if you put those z's through a softmax function at the end of your network and you're actually outputting these activations, then you could instead write the loss more simply like that. And here this is in terms of those activations. Okay, so once again, you have two choices of how you build your network. And for each one of those choices, you have to use the proper implementation of the loss. Okay, any questions on multi-class classification? All right, and so the other application we've talked about a lot is regression. And so we'll just assume you have k different targets. So our likelihood that we focused on before was this additive white Gaussian noise likelihood. And we derived that the corresponding negative log likelihood loss was L2. And so under this model, you would choose L2 loss. I can't remember if we did this in a homework or not, but if you use Laplacian, additive Laplacian noise, then you could actually derive L1 loss, and that's another popular loss for neural networks. Okay. And this is really just sort of a design decision, like you could try L2 and L1, and you could see which one works better with your data set, because you don't necessarily know whether, at least in many applications, you don't know whether your data really does follow this additive white Gaussian noise model. For some data sets, like if you're doing digital communications, then yes, this is probably, or wireless communications is a great model. But for a lot of data sets which are more complicated things, we don't necessarily have a good model. And so this is one option, may or may not be the best. Okay, so we discussed quite a lot. We basically talked about how we can choose these activations, this activation. We talked about how we train this network. We talked last time a little bit about how you choose the number of hidden layer nodes. This again is a design decision. Any other questions kind of about things you're wondering about, like this neural network? How you design anything? Yes?
The ones we review, are they only activation functions, or there are more?
There's definitely more. I'll talk about some more when we get to deeper networks. When you have many layers, the choice of activation is much more important. When you have 2 layers, it's relatively robust. You can use different activations, and it will the weights and biases will learn their way around the activation.
Okay, and our choice of activation function depends only on the like the number of layers or also in the data?
So since we're focusing on two-layer networks here, you can choose any activation that is implemented in the software framework you're using. There's probably like at least 20 different ones implemented. You'll find that there are differences between them, but whether they're major differences, maybe not. A lot of the differences actually come in terms of how these weights and biases are initialized. Because the way that they're initialized, I think we need to talk a little bit more about backpropagation, and then we'll understand a few more things, and we can kind of get back to choice of activation. But yeah, so basically the way that these are initialized, if they're not initialized in a way that is consistent with the activation, then when you start out, it could already be close to like a bad local minima, or it could just be like in a part of the parameter space that's far from a good solution. It may take a long time to converge to a good solution. So these are kind of the things where the choice of activation is actually maybe more related to the way that things are initialized. And if you're smart about your initialization, you can actually make different activation functions like perform much more similarly to each other if they're all initialized appropriately. Okay. All right, any other questions? Okay, so we got to now get into some details with how we train. The first thing we'll talk about is something we could could have talked about back in Unit 6, but we're going to talk about it now. It's variation on gradient descent. And then we're going to get into how we compute gradients with backpropagation, and then we will talk about how we actually implement everything in Python, and then we'll see some more applications, and finally we'll talk about deep networks. Okay, so let's come back to gradient descent, which is sort of our workhorse algorithm. And remember, this is what we're typically doing is we come up with this loss function, typically like a negative log likelihood, and then we want to find the parameters that minimize our negative log likelihood to give us our parameters that we use for our network. And the structure of this negative log likelihood cost is usually a sum over our different training samples of something that is determined by our problem, whether we're working on regression, in that case it might be quadratic, or if we're doing binary logistic regression or multinomial logistic regression, there's some kind of loss here. This loss, the little j compared to the script j, this one works on the level of individual samples. This one works on the level of the entire data set. And I am sneaking in a 1 over n here just to make some of the math work out. As you can see, like if you take this out, it's really just scaling your loss. But having the 1 over n there for now helps to understand some of what we're going to get into. Okay, so this is what we're coming from this perspective, and we have previously talked about gradient descent to solve this problem. And as we know, this is a pretty simple algorithm. So here, this is the teeth iteration of our update. We have the new parameters equal the old parameters minus a small step size times the gradient of the loss evaluated at the old parameters. Okay, so when we plug in this loss function into this expression, then essentially this gradient, due to reasons of linearity, can move through the sum. And really what we have is we have like some kind of scaled average of the gradient of the cost. This is the gradient of the per sample cost. Okay, so here, this is the gradient of the overall, the whole data set. This is like an average over our samples of the gradient per sample. And the key point here is that when we are training neural networks, and especially deep networks, sometimes we have really big data set. So even for a single gradient update, computing this sum, this basically involves computing all these individual gradient updates, could be a very computationally expensive task. And now I think it's a good time to question whether this is something that we should be doing. Because when we think back to how gradient descent actually works, maybe this is our cost function we're studying here. Our initial step is not even taking us in the correct direction. Our initial step is going to take us somewhere in this direction, right? And so if we're spending a massive amount of computation to compute a gradient, which is really not even pointing us anywhere in the direction we want to go, is kind of a questionable thing to do, right? It's like, why do we spend all this computation computing a gradient that's not even pointing us in the right direction? It's pointing us downhill, yes, but it's taking us on maybe a circuitous route of where we want to go. So that's the main idea. Computing the gradient is expensive when n is large, and the question is it worth the effort to compute it precisely? And the answer is no, it's not usually worth that effort. So what is typically done is you work on mini batches. So a mini batch is a subset of your training data. Maybe something on the order of like 32 samples, 64 samples. You might have tens of thousands or millions of samples or billions, but your mini batch is usually quite small. And essentially, you just approximate the gradient using your mini batch instead of using your full data set. So a few more details then is you could say at the tth iteration, roughly speaking, what you do is you randomly select a subset of indices. We'll call that subset big I t. So this is going to be a subset of integers between 1 and n. And we'll denote the size of that subset with like the absolute value sign. So that's the size of your mini batch, so maybe like 32 or something. And then the idea is instead of computing the gradient using this average of all n samples, you compute it using an average of your mini batch samples. So that's really the thing, and we're going to define this as the vector g. And this is not a perfect gradient because we're not using all our samples. We're using just a few samples, so you could say it's like an approximation of the gradient. And in fact, because you're choosing these randomly, you could say that it's like a random approximation. That's why it's called stochastic gradient descent. But anyway, once you compute this g vector at that iteration, you just perform your standard gradient descent update using that gradient approximation. Okay, so that's basically at a high level how it's done. In practice, instead of like just randomly selecting a subset at every iteration, what you actually do is you tend to shuffle your training data set, and then you take things out in chunks. So first you'd use those samples of the shuffled data set, and then the next iteration you use those samples, and then the next iteration those samples. And that way you make your way through all your data once, and then you reshuffle everything and you go again. So that's typically how things are done in practice. We'll talk more about that in a moment. But this is the overall idea behind using mini batches for stochastic gradient descent. Okay, so the wisdom here is that, let's say that I have 32,000 samples in my data set, but my mini batch is size 32. So that means that I'm going through 1,000th of my data set for every gradient descent update. So even though my gradient descent updates are going to be inexact, I get to use 1,000 of them for the same computation that it typically takes me to do one, right? So that's like a massive number of steps I can take for the same computation as one of these very precisely computed gradient steps. And with those 1,000, you are going to get much closer to your local minima than with one step. Does that make sense? So that's like the motivation here. Okay, any questions on what we're doing? Okay, so let's try to justify why this works. So it turns out that this thing we're doing is actually correct on average, or as we know, is unbiased. And we can do a short analysis just using the tools that we know from a couple units back. So if we look at the expected value of the gradient vector at iteration t conditioned on the parameters from that iteration. So here, this is just our expression from the previous page for that gradient, where we are using an average over the number of the size of the mini batch. And here what I'm doing is I'm doing a sum over all n samples, but I have these indicator functions. So this thing is either going to be 0 or 1, and it equals 1 whenever the index of the sum is in the set it. In that case, that is included in the sum. But if the I is not in our index set, then this becomes 0, and that is not in the sum. Okay, so this is just a fancy way of writing this. Summing over I in the big I is like summing over all n, but then multiplying either by 0 or 1 to only include the ones that are in the mini batch. Does everybody agree with this? Is that making sense? Okay, so the reason we're writing it this way is we can actually now analyze what's happening. Because this set, IT, is a random set. So for the purpose of what we're doing here, just imagine that I am randomly selecting 32 indices without replacement, meaning like if I randomly select index 3, then the next time I will never get to select 3. I have to select 6, and now 3 and 6 have been selected, so I can't select them. So basically, if we think about constructing I randomly that way, then when we want to analyze this expectation, we're really treating I as the random variable. That's the only random thing here. This is the only random quantity. It's a random set. But the way that we're building it is even though I is random, the size of I we're treating as fixed, right? So let's say our mini batch is always size 32, so this is deterministic. And then now if you think about, I have a random set, and it's all the entries in the set are chosen uniformly at random. That means that the statistical event, the probabilistic event, that any sample I is in my random set, it's uniform across I, right? Because the way I've constructed this set, it's really just, it doesn't favor any indices over any others. So, right? So the probability that this particular little I that I'm looking at in the sum is in the set is the same as all I. And in particular, the probability is the number size of I over total number of samples n. So again, if my data set was 32,000 samples and my mini batch was 32, there's a probability 1 in 1,000 that each of these i's is actually in that random set that I just generated. Okay, so in expectation, this 0-1 sum ends up equaling this number. And now when you further analyze this, basically this part cancels this part. We're summing 1 over n, n times, so that ends up being equal to 1. And so, wait, did I? No, sorry, I can't remove the sum because of these i's. Okay, but what I can do is I can cancel those. So the 1 over n moves to the front, and what remains is this. And this is actually, if you notice, this is the original gradient expression. Okay, so what we have here is that on average, the gradient of our gradient approximation on average is the true gradient. Okay, now that doesn't mean that it is equal to the true gradient every time. No, it's going to be some random deviation of it. You could even write it this way. The gradient is the truth plus some random noise. You call this gradient noise. But the key property of the gradient noise is that it's zero mean. Okay, so this is what the overall parameters, so the average value of the new parameters given the old ones. So this is our gradient descent update rule. Since we're conditioning on the old ones, we can just take this out of the expectation. And then we have, we just computed this above, which equals this. Okay, so now we have that on average, the new parameters equal the ones that we would have gotten if we would have used the entire data set to compute the gradient. Okay, so SGG updated parameters are correct on average. Gradient approximation is correct on average. Gradient is corrupted by a zero mean gradient noise. And in terms of a picture, it might look like this. So this is gradient descent, where we are, taking the steepest direction downhill every time. But now what SGD is doing is it's kind of on average going downhill, but every time there's this random perturbation, from that average. Sometimes, it goes to the right, sometimes it goes to the left, sometimes it goes backwards, sometimes it goes forward, but on average, it's zero. So this one follows some noisy trajectory and gets down to the bottom. Whereas this one, it really just gets closer and closer to the bottom. This one, once it gets in that region here, it just bounces around. It never settles down. So that's really the biggest difference. If you averaged many, many runs of this, it would look like this, but every single run looks noisy. Okay. So that's the idea behind stochastic gradient descent. To combat this noisiness, you just reduce the step size, alpha t. So basically, the smaller your batch is, the more random things are, and the smaller you have to make alpha t. And as you make alpha t smaller, basically, this looks less and less noisy, but it takes you longer to get to the bottom. I apologize, I just realized I've gone way over time. Sorry about that. If you have not picked up your midterm on Friday, I have the midterms. Feel free to come up. See you guys.